and I would like to introduce then the next speakers. This is Ignacio Fernandez and Juan Pablo Boyero. Both of them are working at the European Commission in the Galileo unit. And Nacho and Pablo, Juan Pablo, I think you have 5 minutes, definitely more, because we have a little bit more time. So use it wisely. Thank you very much, and the floor is yours.
Thank you very much, Werner. Can you hear me?
Read you 5 by 5.
Okay, thank you. Hello, everybody. Good morning or good afternoon, good evening, depending on where you are. Unfortunately, Juan Pablo Boyero cannot join this session, but I coordinated with him for the presentation. So we will use the slot to focus on Galileo high accuracy and Galileo authentication, in particular OSNMA. If you have any question that I cannot answer and is mainly targeted to Juan Pablo, we can take the question offline and try to answer it as best as possible. So let me share the screen. Can you see my screen?
Yeah, we can see it, Ignacio.
Okay, thank you. So as I said, I'm going to talk in the next minutes on OSNMA, or Open Service Navigation Message Authentication, and HAS, or High Accuracy Service, which are the two new services of Galileo. And we are very excited of the current achievements so far and the achievements to come in the next months. I thank also David for the introduction on Galileo and his very interesting presentation, and also leaving some room for me to present OSNMA and HAS. So starting with OSNMA, OSNMA stands for Open Service Navigation Message Authentication. It is a mechanism to authenticate the Galileo data used to calculate a position, mainly the ephemerides and the clock corrections, and as well the status flags, the time transmitting the signal, and the ionosphere and other information required for calculating the position. It is equivalent to a Galileo digital signature, although it's not exactly a digital signature, as I will present later, and it is transmitted in 40 bits every other second in the INAV message, in the A1B component at the 1575.42 megahertz. As you can see here on the right, there is this OSNMA field where we transmit the OSNMA information. Another property of OSNMA is that it makes the signal unpredictable, and this is important if we want to protect not only the data but also the signals against replay attacks. A question that we ask ourselves still, and we asked ourselves at the beginning of OSNMA, was why is Galileo, or why should Galileo implement OSNMA? And the answer to that is the threat of spoofing. So we talk a lot about jamming and spoofing. We see a lot of jamming. We don't see that much spoofing yet, but we know, I would say by now, everyone in the community, how easy it is to spoof the GNSS if it is unprotected. And we also are aware of some cases. Sometimes the cases that we see out there, we are not sure if they are spoofing the application or they are spoofing the signals, but there are cases where we are sure that the signals were spoofed. And this is one of them. It occurred in Shanghai a few years ago. And as you can see, the position, this is the position extracted from AIS from vessels. And as you can obviously see, the vessels that are reported here were not in ground, they were in a river, but their position was falsely reported. And it was not just a repeater, but a position that was moving around. So how does it work? OSNMA is anchored in a public key that is transmitted by the GNSS Service Center. So the GNSS Service Center uploads this public key or equivalent, and this is downloaded. This has to be downloaded and stored securely in a receiver, and this is where OSNMA anchors the protocol. So then, based on that, in the signaling space, we transmit several layers, as with most cryptographic protocols. We do transmit digital signatures, but we also transmit what we call a Tesla key and message authentication codes. And thanks to these layers, we are able to authenticate the navigation data. Thanks to this information, the receiver can verify whether the data received matches the authentication information, and if so, it can trust the data for positioning. So this is a scheme of how it works in a little bit more detail, although not full detail. If you want the full detail, you can consult the OSNMA signaling space ICD and receiver guidelines. So we start with the public key, and then every few minutes, I would say, we receive a root, a Tesla, what we call a Tesla root key, which is a key of the so-called Tesla protocol. That is the protocol that we use for OSNMA instead of plain digital signatures for performance reasons. So there is a root key that applies for a period that can last up to several months. And once the receiver has the root key, it can verify it with the public key that it has already in its possession. The next step is the receiver continuously receives the navigation message and the tags. And then after receiving a tag for a certain navigation message, it waits. And after some seconds, in the order of 30 seconds, it receives a Tesla chain key, which is a key part of the chain that finishes in the root key that I said before. And the authenticity of this key is verified with the root key through a one-way function. Then once the Tesla key is verified and therefore is trustable, the receiver can proceed with the computation of the tag. And then the last step is to compare the computed tag with the received tag some seconds before. And if they match, we can consider that the navigation message is authenticated. These are, in short, the steps followed for OSNMA. If you want more detail, please check the ICD. We are glad to say that OSNMA is available in test mode, but available already since about a couple of years ago, although in test mode. And available meaning highly available. In particular, we see that availability of authentication of the INAV message of at least 4 satellites is very high. It's in the, I would say, high 99% worldwide, meaning that we do not expect that the availability of the open service is degraded or sensibly degraded due to OSNMA. In terms of accuracy, let me show briefly a plot from ESA testing showing the results of OS versus OSNMA from last year in different stations worldwide, where we see that there is a slight difference, but in the order of centimeters, and mainly due to the fact that in some occasions not all satellites in view are authenticated by OSNMA, so this leads to small divergences in the accuracy, but we can fairly say that accuracy is not degraded, not significantly degraded by OSNMA. In terms of next steps, we just published the service ICD and guidelines. So before, in the last years, we had published testing ICDs. In December last year, we published the service ICD and the guidelines, meaning the description of the specification that we will transmit when we declare the service operational. We expect to switch the signaling space from the public testing ICD to the service ICD in the next weeks. Actually, it is foreseen in June 2023. We will see if we are on time, but in any case, it's quite imminent. And this will imply that there are slight changes to the signaling space definition, as I said, already published in the ICD, that will be implemented in this time in the signal. Then what will follow will be the publication of the operational cryptographic data, the public key that I mentioned before, and other cryptographic data that I didn't talk about, but is also relevant. And this will happen after the summer. And then the step following that will be finally the initial service declaration, which is foreseen by the end of 2023. So if everything goes well, we expect that before the end of the year, we will declare OSNMA as a service. So that's all concerning OSNMA. Now let me talk about the Galileo High Accuracy Service, or HAS. Galileo has provides precise corrections with the purpose to do precise point positioning worldwide and for free. In particular, we provide corrections for orbits, clocks, code biases, and soon we expect to provide corrections for phase biases as well. We correct the Galileo INAV message. In particular, we provide biases for E1, E5A, and E5B. We also provide biases for our E6 signal, and we provide corrections for GPS as well, in particular L1CA, and then L2C and L2P. We hope we can provide soon for L5 as well. The corrections are disseminated through the E6B signal at 1278.75 megahertz, and we also broadcast the corrections through a ground dissemination channel following RTCM-like format, in particular SSL. So you can see in the bottom of the picture a scheme of how HAS works. We have, at the moment, HAS based on the GSS stations, so the Galileo sensor stations, which are only 15, if I'm not mistaken, at the moment, with the recent addition of Wallis. And we expect this to be increased over the next years with additional stations dedicated to HAS. The corrections are computed in the HADG, or High Accuracy Data Generator, located in Torrejón, Madrid. And then, as I said, broadcast through the signal in space and through the internet for registered users. In terms of current status, we have three phases of HAS. Phase 0, which was a testing phase. Phase 1, or initial service, that, as David already mentioned, is the phase where we are already since the initial service declaration that took place on the 24th of January of this year. And then the next step will be phase 2, or full service. The HAS-6 ICD is already available since about a year ago. We have already received some comments. We know people is implementing it, and we are very excited that many major companies and important applications are very interested in HAS. Next step will be to publish a baseline user algorithm for doing PPP with HAS corrections. It will be just a proposal out of the many ways that the HAS corrections can be used, because PPP algorithms depend on what the users want to do, but it will be a baseline that hopefully will be useful for some applications. And then we will continue with phase 2, which will provide global coverage. We are not yet providing global coverage, although we are close to it. Better accuracy thanks to more stations, ionospheric corrections in Europe to help convergence, authentication, and error characterization. In terms of performance targets for the different phases, you can see the summary table here. Starting with phase 2, if I may, our target is an accuracy 95% of 20 centimeters and 40 centimeters horizontal and vertical respectively, and a convergence time below 5 minutes worldwide without ionosphere, and below 100 seconds in Europe with ionospheric corrections. This is phase 2. In phase 1, we are providing an accuracy that is already very good, but we are not providing globally the accuracy that I just mentioned, and we are not providing ionospheric correction. So therefore, the TBCs that you can see in the table. If you want more details, you can consult the SDD, service definition document, that was published together with a service declaration, where you can see that the minimum performance levels are somewhat relaxed at the moment because we are in this initial phase, although the performance is very good, as I'm going to show in these slides. So this is the performance of the products calculated by Ilaria Martini, mainly with the help of some of us. So you can see, for example, in the top left figure, the improvement of the accuracy of the radial error between the OS and the HAS. So you can see in the PDF a significant improvement. You can see here the aggregated SISE, signal in space error, where you can see also that most of the occurrences are in lower errors. And if we go to higher probabilities in the CDF, you can see that the difference is even higher. We have also seen that HAS is able to detect some clock runoffs with I mean, in a matter of seconds, because it's monitoring the signals with a few second latency. If you want more details, you can consult the paper. And in terms of user performance, without explaining all the details, I can show here that this data campaign comes from last year, and it was based on a network of stations worldwide, where we can see the performance in Europe, America, and Asia. Performance in Europe, you can see here, at user level, is pretty good, and even better than the expected accuracy of 20 and 40 centimeters, 95%. If we go to the Americas, the performance is somewhat degraded, yet in the few decimeter level, and very close to the target. And if we go to Asia, due to the lack of stations, the performance is somewhat more degraded, especially the station called Tata in Taiwan, as you can see in the plot. I have to say that we have a new station there, the Wallis station, and we will have more stations soon, so we hope the performance can improve quickly. Let me say that the number of stations for HAS is very low. I was talking about 15 stations compared to normal PPP services that are providing, that are using hundreds of stations sometimes, so the results we find quite remarkable. In terms of summary of the presentation, as I said, OSNMA offers data authentication and signal predictability for Galileo. It is already in the signaling space, and it is expected to be declared operational by the end of the year if everything goes well. Regarding HAS, it is a PPP correction service provided by Galileo, and it is currently correcting GPS and Galileo itself, and it's aiming at an accuracy of 20 centimeter, 40 centimeter horizontal and vertical, respectively, at 95%. And we started the initial service provision operationally in January of this year. Since then, I have to say that the performance is going quite well. Next steps are declare the full operational capability of OSNMA and HAS, as David already presented in his previous presentation with the overall roadmap of the services. And then a major next steps concerning authentication is the provision of spreading code authentication in the E6, hopefully very soon in the next couple of years. So this finalizes my presentation. I hope I did it on time. And thank you very much for your attention.
Ignacio, thank you very much for this very interesting part, especially the exciting results you have achieved with the HAS PPP with this number of stations, really remarkable. And I think there are also a lot of questions. Again, thank you very much for that.